Hello, everyone, and welcome back to another episode of Solidity Fridays. Today, I'm joined by Myles Traut, who's a Solidity developer of Linum Labs, and we'll be covering the Superfluid. Starting our series of the Superfluid protocol. Hi, Myles. How are you doing?
Hey, good morning. Good morning. I'm good, thanks. How are you?
Yeah, very well, thanks.
Yeah, happy to be streaming. First one of
Yeah,
the year.
yeah, season 3. Very
Oh
exciting
yeah.
stuff.
Yep. Starting off with Superfluid.
Yeah, so they allow for streaming crypto payments. And it is quite complex. So we thought it could be a series because they have several different ways of streaming. And we could look at the different ways in different episodes, and then maybe some examples of how to integrate Superfluid into your own application using Solidity.
Yeah, awesome.
Um,
So it seems that automation in the blockchain is quite the narrative this year because
mm,
um, because I see a lot of protocols are starting to come up with different ways to automate different things, and this is just a new way to automate um, ERC20 transfers.
yes, yeah. Yeah, I think that's a very astute observation that it's becoming like a theme of the year is the automation and blockchain.
Mm. Um,
Here are their
I,
docs. So there's two ways of streaming. One's called a constant flow agreement, and the other one's called an instant distribution agreement. Myles probably knows a bit more about me, more than me about the differences. But a constant flow agreement basically lets you stream money constantly in like in a flow.
yeah, in a
Um,
I think it's amount per second that you can stream for a specific set of time. So you can set it to stream for a month, and it will work out the flow per second based on the amount that you want to stream.
yes,
That's the
awesome.
CFA, yeah.
So I
And
think that's what we'll be looking at today. But then if you want to just talk about the IDA.
so yeah, the IDA is more. It's pretty much the opposite of the CFA, where you can basically set a lump sum to be paid um, at different time periods. So once a month, you can set a lump
I
sum to be
see.
paid
So that's
from
nice for like
one.
a salary.
Yeah, and you can go from one account to many accounts
Oh, cool.
in one transfer, in one transaction, which is pretty awesome.
Mm. Yeah, it's a very cool protocol.
Oh yeah.
Um, I haven't looked at the super tokens. I just want to see if they cover everything.
They,
I
I
have to
think
develop code that interacts with super code. Oh, okay, this is just to interact with it.
I think this is
Oh,
an episode all by itself.
yeah, that could actually be a whole other episode. Um, it seems like you make a wrapper and
Mm.
then, but yeah, cool. Um,
I really enjoy things that um, uh, add on to what's already been done. So like an ERC20 has been an ERC20 since the beginning of time, and these guys are kind of building on top to add new um, what's the word I'm looking for?
like functionality.
New functionality to ERC20s, which I think is awesome. It's really
Mm,
like innovation is it's really cool.
it is awesome, yeah. It's really cool. Cool. Should we dig into some code?
Let's dive in.
Um, so let's look. This is their main repo. I think it's called their protocol mono repo.
Mm-hmm.
It's huge. While we're here, I'm actually just going to quickly start. Cool. Ethereum contracts
Contracts, yep.
we probably want. And then I'm just going to open up the interfaces in a new tab.
Okay.
And then, so we're looking at the two types of agreements for streams in the next two episodes. it's kind of been a series, if you think about it, of all the streaming protocols, because we looked at Sablia last year, and they're very cool, but you have to do like send the payment as a batch, like a bulk payment of the total amount in the beginning, which kind of defeats the purpose a bit. And then you guys also looked at cask finance.
Yep.
In the last episode last year. And now we're looking at Superfluid, just like a comparison of all the streaming payment platforms I could find. And I think we left Superfluid for last because I think they're the most complex, but also probably the coolest.
Yeah, definitely the most complex.
Yes, yeah. Sablia V2 is coming out soon, though, so that'll be an episode we can do, and I'm sure they have some cool new things coming. Awesome. So this is for the constant flow agreement. And
okay.
It's the V1, and they import a lot of stuff from the interface, superfluid.sol. So, but there'll be...
Yeah, there should be an interface for that.
And then I'll open the agreements interface. Cool. So it seems like they follow the standard of their NatSpec isn't really in the... or like the implementation notes aren't in the contract itself. It's all in the interface.
How do you feel about that? Is that like, do you mind reading it in the interface when you're going through it, or would you prefer to have it in the actual contract?
I prefer it in the actual contract by far, just because I don't want to have to jump between two things. Also, sometimes like this first function might not be the first function in the interface, and then you have to search and find it. So I find that a bit arduous. I don't know why people actually do it. I guess to save space, but it makes sense because you are interacting with the interface most of the time and not the contract itself. But I much prefer to just have it. In an ideal world, I would have it in both, or in the contract. How do you view it?
No, I think I'm with you on that, because as I'm going through the contract, I prefer to read the NatSpec, whereas the interface, I'd go through it, but the most of the time I'll be looking at the contract when I'm interacting with it.
Yeah, to see what's actually happening.
But I see why they do it to save space and kind of clean up the contract and make it look neater. But yeah, well, like you said, it's super annoying when the first function in the interface is not the first function in the contract, and you have to go and search for it. And that can eat up time. Whereas if it was just in the contract, you save all that time.
Absolutely. Cool. So the contract is over here. It inherits agreement base and constant flow agreement V1. So that's the interface. I don't know if we should look at agreement base quickly, actually.
Yeah, let's maybe take a look.
And then we can look at the interface to see these errors that they've commented out below. Oh, cool. So this is an abstract contract that's probably giving it the upgradability. So it's a UPS proxy upgradable pattern. I don't know if we've covered much UPS.
No, we haven't.
On Solidity Friday, so that could be a cool thing to look into and explain how it works. But okay, cool. This is just actually the proxy. So they have this agreement base, and then this is the contract that'll like delegate call to the actual agreements that inherited. So then you can update and upgrade the agreements later on, so they can have a V2 using the UPS pattern. Very cool. Right. Now let's maybe look at the interface. So I see this interface is actually an abstract contract itself
as well.
And it inherits iSuper agreement. It's interesting that they chose an abstract contract and not an interface, because abstract contracts can't have state, but it's also, it makes sense that you can use either. Okay, so this is a bit confusing because the implementation notes for all the functions are in the interface, but the errors in the interface, but the explanation for the errors are in the contract.
That is weird.
But
So
yeah, so
we have to jump between them.
yeah. But
I
yeah,
suppose
let's
we could.
maybe.
Yeah, I was gonna say we could just stick in these because these errors are the same in the interface as they are here in the NatSpec, right?
Yeah.
So let's just maybe you could just check these out.
Yeah, cool. So there's errors for when a sender cannot create flow or update or delete as the flow operator.
Yeah. So yeah, a flow operator I found out is basically the contract that's been approved to operate on a EOA.
I
So
see.
yeah, it's just basically the same as a transfer from works where you have to approve a third party to interact with your funds. That third party would be the flow operator.
Okay, very cool. Flow rate allowance is exceeded. We'll see that error later, and it'll make more sense. Then operator does not have permissions to create, update, or delete flow. And we'll see what gives the permissions later to do so. And the sender cannot set themselves as the flow operator. Fair enough. You have the third party, as Myles said.
Yeah, that makes sense. Yep.
And you cannot set a negative allowance. Fair enough. Cool. So they have some constants, and constants get set not in the constructor like immutables. They get set here like inline. So they have a default minimum deposit, a maximum deposit, which is int 96 dot max, cast to a UN256.
Finally, the default minimum deposit is not 0. It's, I assume that's 0 point something. It's 1 with
1 cost 2 to the right.
yeah,
Sorry, 32 to the
32
right.
to the right, yeah.
And then cost to a UN96, which is then cost to a UN256. Yeah, it'll probably be close to 0, but
not exactly 0.
Yeah. We could probably spend a whole episode just talking about this, actually. But it's not. They have a max flow rate. Cool. Then they have some byte32 constants, which are just catch-acks of different things. So it's basically just saying there's a config key and then there's a minimum deposit key. So that's pretty straightforward. It's just a hashing of these strings, which is just what they're basically making the key for. They're just hashing that with the Ketchak 256 algorithm. Okay, now they have an immutable constant flow hook, constant flow agreement hook, which will probably be set in the constructor because it's immutable. Then they have a gas limit, which is 250,000, which is nice and high. They say it's arbitrarily chosen safety limit for external calls to protect against out-of-gas grief exploits, which is great, but interesting that it was arbitrary.
Yeah, that is interesting. I mean, it would be annoying if your stream ran out of gas.
Yeah, true.
Do you think that's for like third-party exploits?
Yes, it is to, I think, stop people from doing kind of like a denial of service where they make you, like they just
burn all your gas.
Yeah. Cool. Then they use safecast for both int256 and UN256, and we'll have ints because things can be negative here. We'll see later. A few structs, a flow data, which is a timestamp, a flow rate, a deposit, and an owed deposit. Flow parameters, which is a flow ID, which is a byte32, so that'll be probably also a Ketchak hash. a sender, a receiver, which are addresses, a flow operator address. So we have three parties in every stream of payments in the CFAs. And we have an int96 flow rates and a bytes, which is user data, which, I think we'll see that later.
Yeah.
Flow operator data. So they have permissions. And I've been seeing this quite a bit. It's actually done in Aave, where it's a uint8. And then they make a bitmap, of all the different bits, and then the first X amount of bits will say like if it can do the I don't know, like send, and the next bits will say if it can receive.
Yeah, especially update. So you can update the stream or delete the stream or create.
Okay, so those are the three options. I see.
There's a few more, but those are the main ones.
Okay, cool. So yeah, that's quite a cool thing that people are starting to do.
Yeah, I love how they do
that. It's quite a tricky thing, but it's very cool. And then they also have the flow rate allowance, which is an int96, so that can be negative. Cool. So yeah, the constructor, they set their host, which is an iSuperfluid, and an iConstant flow agreement hook address. And it overrides. Pardon? So
I was gonna say it seems the host contract is like the brain of the operation, and only it can call everything else, which is why they pass it in the constructor.
I see. So that would obviously be deployed first.
Yeah.
And I think we will look at that iSuperfluid and the Superfluid contract itself, that like brain contract.
Mm-hmm.
But I think in a later episode, we decided to take a bottom-up approach and look in detail at the agreement contracts and then at the brain, not the other way. Where we usually, I usually when I look at a repo, look at the main thing and then I look at everything that uses it, like and go down in depth thereafter. But Myles and I decided with this, it might actually be easier to look bottom up. And
the other way.
It might make more sense, yeah.
Mm.
Cool. And then it's an agreement base where you drop in the address of the host and you set the hook address. What do they mean by hook? Because I see that there's for constant flow agreement hooks. Do you know, or will you have to look at that?
Yeah, I've seen the hook contract. It's just before. I might be wrong about this, but it's a before stream hook and an after stream hook. So when something before the stream gets initiated, you can do something, and once the stream closes, you can do something. I think.
Okay.
I think so, if memory serves me correct. But it's in that vein of functionality.
Okay, very cool. Cool. Now we can start with the functions. Yeah. So real-time balance of.
I think this is pretty awesome. Getting a real-time balance.
It's so cool. So it takes in the token, which is of type iSuperfluid token. So that'll probably be a wrapped token.
Mm-hmm.
The account, which is the address, and a time, which is uint256. It's external, it's view, it's overridden, and it returns a dynamic balance, which is an int, so it can be negative. A deposit and an owed deposit. And we'll look at it now, but I just want to see the NAT spec for it. I mean, the implementation, if it's... See, so these aren't in order. But luckily I copied it, so let me... Real-time balance of... Oh, it's not in the... Wild.
What?
It's not in the iConstant flow agreement.
That's crazy.
Oh, it might be in iSuper agreement? Yeah. Okay, so back to interfaces, agreements.
Like, you really have to plan a repo like this before you start
the project,
right?
I'm sure they spent like months on
just like setup and admin and like...
Yeah, they probably have extensive like architectural like blueprints, and then they start.
It's like the pre-production on a movie.
Yeah, absolutely. Except with
except with
GitHub responsibility.
Oh yeah.
Here's real-time balance of. So it calculates the
There we
real-time
go.
balance for the account of this agreement class. The account is the account the state belongs to. The time is, so like the instantaneous time that we're doing this calculation at. It returns the dynamic balance portion of real-time balance of this agreement. And what that means is, so I don't know if we should go into this now, but there's different
different portions to a total
yes,
balance.
it's like set. It's like a stream has different phases, and this phase is, so the dynamic part is when it's like it's got an available balance still. So this kind of reads right to left. So you have an available balance, and then you go into like a buffer period where you have an extra amount, and then you go into like another period where you can be liquidated and you no longer have a balance. Where was I? Here. So yeah, we'll look at that maybe in a bit more detail soon. But basically, there's 3 different sections of a stream, and we're getting the real-time balance when it when it's still got a balance, like a valid,
Yes,
available
like a valid
balance.
balance.
Yes. Cool. So it first gets the flow state with the token and the account. So and that's probably, it's checking, we can look at this function now, but it's probably checking that it is a valid state of the and that will return a bool, which is exist, and struct, which is the flow data, which memory when we call it state. If exist, actually maybe we should look at this function and then see how it does this. They call it lots. Here.
Okay.
It takes in a token and an address of the account. It's private, view, returns, we know what it returns now. So the data is, it gets the, it says byte 32 array, and it's token.get agreement state slot. So remember, they have wrappers over tokens, so they have extra, Superfluid tokens have extra functions that ERC20s don't have, like Myles was saying, they've built up over it. So they do this, but I don't want to look at that because it's in a different contract. But basically, they just get the slot. What's at the actual slot, and then they return decode flow data, and they take the first element of that array and cast it to uint256, and then pass that into decode flow data, which might be worth looking at. Okay, so this takes in a word, which is a uint256, and it's probably going to do bit operations if we're calling it a word. It's internal, it's pure. It returns the bool. Okay, so this is actually returns the exist and the flow data, and then it passes that to the previous function, which then passes it up to the get balance.
Sure.
Okay, so first what it does is, this is how we get the bool, is it says, is word A greater than 0? Fair enough. And we'll probably often get true. If true, so it gets the timestamp by casting the word A. So a word is usually, I don't know if this is exactly what they're doing, but a word is usually, I think, 8 bits.
Yep. Yes.
1 byte.
I think you're right.
And then they move it, they cast it to the right by 224, and then shift it to the right by 224, and then they cast that to a uint32.
Yeah. So you were saying there's 256 bytes in 1 bit, or is it 8 bits?
It's 8 bits in 1 byte.
Okay. And then there's so the 200 they're moving their bit mask basically over 224 bits. And then the last section would be the timestamp.
Yes.
Oh, yeah. That's awesome. This bit masking is such a new thing to me. And I must say, I'm really starting to see the functionality of it. It's so cool.
It's amazing. It's really amazing. Especially when you look at how they use it for permissions. It's really cool.
Yeah.
I think I was wrong though. I think it's actually in one word, there's 16 bits. So it's 2 bytes per word.
Okay.
So we take 16 bits and then we move them. Yeah. Cool. Then it gets the flow rate by combining the max uint 96 with word A, now shifted to the right 128. And then we cast that to an int, and then cast that into a small int. Or we cast the whole thing, sorry, into an int 96.
Everything, yeah.
Yeah. Because we are upcasting, they say, from type uint 96.max to uint 256 to int 256, we do not need to use safe cast. That's interesting because, okay, that makes sense. But it's just interesting because they say using safecast for int 256 and uint 256. So how do they indicate that they're not using it? Yeah, I wonder. Cool. Then now we've lost some bits to get the flow rate over here. So now we get the deposit, and we shift word 8 64 bits to the right, and then we combine that with the max of uint 64. We shift that to the left 32 to recover the clipped bits. Okay. And then we do the same for O deposit.
That's shifting the entire thing 32 bits.
Yes.
Interesting.
Cool. Oh yeah, see, this is what I was saying. We're like,
yes.
You'll have a word, so we know we have 16 bits, and then we have a reserved. Oh, but this is a uint 256. Sorry, it's not 16 bits. It's a uint 256, of course, because that's what we passed in the original function.
Yes. Yeah.
So we have 256. I was wondering how they're shifting 16 by 224, because then you'd lose the whole thing.
Yes.
I was quite confused a few minutes ago. Okay, cool. So we have 256.
And it seems the first 192 is reserved for the data.
Yes, reserved for the data. Then this is the patrician period. So we can go into this later, but the patrician period is basically when you're starting to run out of your balance, basically. And that's for 32 bits. And then the next 32 bits is liquidation period. And then, but we'll look at this. Sorry, I just got excited by seeing this bitmap. Let's go back. Where were we? Control F, balance of
get real time balance of. That's what we were. The very first function.
Yeah, let me just actually scroll up. Wow, it's quite a long contract. Cool.
Okay, awesome.
Cool. So that's the first function. Done. Cool. Then we have an internal function. And I know it's internal because it has this little underscore. Oh, and it says internal here, but they're following that convention. And I do like that convention.
Yeah, me too. Me too.
Should we see what this does?
That's awesome.
Oh, we changed to this one. So we go to interfaces, agreements. Oh, interfaces.
Just by reading the name of the function, I would assume it works out the flow per second given for a given amount.
Yes. Oh, and this one also is in a different contract. So let's not look for the thing. So yeah, I think you're right. That makes sense to me. So
Rate deposit can't be greater than maximum deposit. That makes sense.
Yeah. and it reverts, and they're using custom errors to save on gas. It doesn't save on much gas because it only saves on gas in the worst case when you revert, but it's still.
It does save on contract size though.
Yes, it does save on contract size. That is true. I remember when I made that huge contract and you had to make it smaller.
Yeah.
For my requires and made them custom errors.
And this is a big contract, so I think they'll be looking to save as much size as they can.
Absolutely, makes sense. And it's not like a diamond or something. They're using UUPS, so they do have size limits. Yeah. Cool. Deposit equals clip deposit number rounding down. Cool. That's probably just like a rounding function. Flow rate 1 is deposit divided by liquidation period. Okay. That makes sense because you have this amount you want to send. You have this amount of time you want to send it through. So if you divide this by this, you should get the rate.
Yes.
It's like rate is distance over speed, but over time.
So liquidation period could be a month, and your deposit is 1,000. So you'd want to send that entire 1,000 rand to someone over the period of a month.
Yes.
Yeah, and that would work out the rate. Okay.
Cool. And then they do some casting of flow rate 1 into an int 96. And that's that function. Then they get the deposit required for flow rate pure. So it's the same.
Yeah, I think this is
like the opposite. Yeah, so it'll just change. So they first do their checks, and then there's a calculate deposit function, which is an internal function that takes a flow rate and a liquidation period. But Myles is right; it's just going to be the reverse of this function. Well, not the reverse, but the switching.
Yeah,
so deposit will be there and flow rate will be there.
So yeah, this one you basically.
Well, actually, liquidation period will be on top. And then flow rate will be on the bottom in an equal deposit.
Yeah. So this one basically you give it a flow rate of like how much you would want to send to someone in a month, and it works out how much deposit you have to give in order to get that rate.
Okay, cool. Then we can get the maximum flow rate from deposit. Similar thing.
It's just a view function.
Yeah. And then another view, get deposit required for flow rate. So it's the same thing, but instead of being pure, and it probably.
I think these do the calculations, and that's just to view whatever's returned from these.
I thought so too, but look, it actually does something it does eventually call it, but so this can't be pure because it's doing stuff, it's changing state. So it gets, so the host also does some governance. But I think that we can look in another episode.
Yeah, I think that's an episode on its own too.
So let's go over here. So let's talk about liquidation and solvency before we carry on. So when opening a stream, the protocol will take a small buffer or deposit. So it's this is how they do it. Sablier take the full amount in the beginning, and these guys take an extra buffer or deposit, and leaving their streams open for too long, stream creators stand to lose this buffer. This mechanism creates the main incentive for users to close their Superfluid streams before running out of tokens. It is a user's own responsibility to close their stream. Super apps can also draw an owed deposit, allowing them to open a stream of the same size without needing an initial balance. I see, that's what that owed deposit is. So then the general flow of solvency states for super tokens in a constant flow agreement. So firstly, you're solvent, and that's when you have a balance greater than 0.
So wait, just to pause you there. Going back there, you're telling me I can open a flow on credit, basically. And that's what this owed deposit is.
Yes.
That is awesome.
It's so cool. It's really rad. Yeah. It's a really cool protocol.
That is so cool. Oh, man. Okay, sorry, continue.
No, it's chill. So once my balance reaches 0 or goes below, now things are critical. And the permissions on the stream now allow anyone to close it. Until the stream is actually closed, funds are paid to the receiver's wallet using the sender's initial buffer. So now you're starting to lose that deposit. The critical period is subdivided into 2 sub-periods. The first one is the partition period, which starts when the stream becomes critical. And that's set by the governance parameter. And then the second one is a plebs period, which spans the remaining time frame until the stream becomes insolvent. When the stream is closed, any remaining buffer is taken and assigned or distributed to either the PIC or a pleb. If the stream is closed during the plebs period, we call the account closing the stream a pleb. Do you want to explain what a PIC is?
Sure. So a PIC just stands for a patrician in charge.
Yes.
And it's a person that is selected, or the user that is selected, to basically monitor streams. And if a stream goes critical into that beginning period, into the patrician period, only the patrician in charge is able to shut down the stream. And then that buffer, that deposit, goes to the patrician for shutting down a stream that's in critical period. A pleb is just a normal user. Anyone can do this. So after the patrician period, the patrician hasn't closed the stream. It goes to the pleb period. So it says anyone who can see the stream is insolvent can now close it, and they'll get that buffer reward.
Yes, okay. That's a nice side hustle if any of you are looking for one.
Yeah. You just got to monitor streams.
Yeah, that's really cool. Thanks for explaining that.
Sure.
And then from there, after critical, you can become insolvent. And then, there's a deficit. And then that's when you take the slashing fee. So that's basically what Myles was saying. Yeah, so now we can come back here. Now we know what a partition period is. So this function just sees if it's the partition period now, I think. So it takes in the token and the address, external view override, returns bool is currently partition period, and uint256 timestamp. Okay, so it calls. So host.get now is just getting the timestamp.
Getting the timestamp, yeah.
And then it returns that, but it firstly returns this bool, which is this function. It calls is partition period, which takes a token, an account, and a timestamp, and returns a bool. It's just if available balance is greater than or equal to 0, return true. Which is they just take the first return parameter of get real-time balance of, which we looked at.
And then that means you're solvent. That means you're good.
Yeah. Cool.
It would be great if you sign up to be a patrician and you had to change your username to Patricia.
That would be great. Cool. And then this function calls an additional function, which is an internal function called is partition period. It takes in the remaining available balance, which we get over here on line 210. The signed total CFA deposits, which they get. It's the account state. Which they get from get account flow state, which we'll see probably later, which is a internal function. And then they get deposits.toInt256. I wonder what it is before. And then they put that in as the second parameter. Then they get the liquidation period, which they get from decode 3P's data token. So the 3P's is the pleb, the partition, and the pirate. Yeah. So pirate is the last one. And then they take in the partition period and return a bool. And then that gets passed into this function. Cool. Cool. Let's see how they create a flow. So they take in the token, the receiver, the flow rate, and some data, which is the CTX. So that's probably context. And that's in call data. So just a bit of an aside. I was talking to a friend recently about call data, and so on a layer 2 blockchain, you want to minimize the amount of call data you have, and on a layer 1, you want to minimize obviously the amount of computation size you have, but you often do that by using more call data. So this must be, they probably I don't know what chains they've deployed this on, but this is probably going to be a layer 1 vibe, unless it's just an unavoidable call data, because sometimes you do need a context. I know sometimes with UPS, I think you do need contexts.
Do you know why that is? The layer 2s prefer to have low call data, low amounts of call data.
I don't know for sure, but you can't.
I mean, it's cool. I can look it up when we're done, and we can get back to
sure.
it
I
in
actually have
part
a
2.
tab open on it. But it has to do with like the compression. I think you can't compress a function. So.
When it moves from.
So rollups have cheap execution but expensive data and availability costs. So like I know Optimism is really good at compressing data, but most like ZK rollups and stuff, you can't compress data too easily, especially when it's call data.
Oh, that makes sense. That makes sense because they've got to roll up a vast amount of data now to push up to layer 2. Oh, that makes a lot of sense.
So yeah, as we transition to a layer 2 world, call data goes from the cheapest resource to the most expensive resource. Wild. Cool. And it returns a bytes memory new context, but it also makes the flow, so it can't be a pure function. Cool. So it gets the current context by calling authorized token access from the agreement library. So you pass in the token and the context, and you authorize that token access for the agreement. I don't know if we should look at the agreement library quickly, or if we should just.
We could.
I mean, we assume it authorizes the token access.
Yeah. We could. Yeah. Let's look at it. I saw when they implement projects, they interact with the agreements via the library, and the library is in apps.
Thanks. Wow, you know this repo quite well. It's probably CFAV1 library.
What was that library called? I can't even remember.
Oh no, it was called Agreement Library.
Agreement Library, interesting.
Yeah.
Did they instantiate it somewhere in that contract?
No, they didn't seem to. Oh yeah, they would have. Yeah, it is.
There we go.
Cool. So this is what we're looking at. Authorize the message sender to access token agreement storage. I see. Note message sender must be the expected host contract, and it should revert on unauthorized access. So they used requires for that. Yeah.
Okay.
Cool.
So it's just basically authorizing the host to work to be able to create the flow.
Yes, and that's the first thing they do. Then they have a memory state variable. Well, no, not a state variable. Local variable called flowVars, which is. This is so weird. Where does this?
Stack vars.
Yeah. Stack variables, create or update flow, memory flow variables. I just want to see where they.
Yeah, where's that?
Oh, here it is. It's a struct that they define later on. It takes in its token, a sender, receiver, and a flow rate as stack variables for create or update flow function to avoid stack too deep issue. I see. Okay.
Oh.
Let me go back to the first case of it. It's probably create flow. Cool. Flow variables. So now they've got this. They instantiate an instance of the struct, and they set the token, the sender, the receiver, and the flow rate using the from the current context. And then the receivers, just the receivers passed in, and the flow rate passed in. Then they get a new context equals create flow, passing in the flow variables, the context, and the current context. So this is the context before, and this is the current context is in the
After, yeah.
after the authorization. Should we look at this create flow internal function?
Yes, please.
Cool. So it takes in stack variables, those flow varies. Oh yeah, we've seen what it takes in because we just passed it. So it creates or update flow check. Let's look at that. So this will be probably a check of if it's valid.
Yeah, or if there's permissions, if the user has permissions.
First checks that it's not a zero address receiver. Fair enough.
Important.
Cool. Then they set all the flow params. And then, yeah, and then it has these two if statements and it does the checks. So it checks no self flow and that it's a valid flow rate. Then
so basically, instead of sticking 100 requires in this function, they just put the internal and do all the requires in that check or update. That's cool.
Yeah, I like that. Cool. Then they get the agreement data. That makes sense, and that returns a bool of exists. I think we've seen this already.
Yeah.
And the flow data struct. And then if it already exists, revert. Fair enough.
Yeah.
Cool. And then if...
Oh, this is super app things. I'm not...
Yes. I think we'll look at super app in its own
yeah, definitely
episode, but
I want to say it's an app built on top of this Superfluid contracts that kind of interact with it, that they have out the box. I might be wrong, but from what I've read, I think that's what super apps are.
Yeah, I think you're right. They mention it here. Super apps allow us to build smart contracts that are fully integrated on the protocol level. Incoming streams, super app, custom outgoing streams. I see. You're right. You're absolutely right. Cool. And then, okay, so if it is an app, you make the new contacts and you change a flow to an app. So if you set, you want this to actually be an app, like an intermediate contract, then you change it to an app, else change flow to non-app, and then it's just the flow.
And then it's just the flow. Oh, awesome.
I would like to look at this change flow to app function though, just to see how it...
How?
They call it a lot. Wow. Function.
Okay, yes.
So it first has a struct vars change flow to app to avoid stacks too deep issue. Yeah, because look, they've already got a lot of parameters passed in. So they pass in this this struct to avoid this being a stack too deep. Cool.
It's genius people that work around these errors.
Yeah, it's really cool.
Oh.
Takes in the address app to call back. Okay, that makes sense because we're going to use a probably like a delegate call. iSuperfluid token, flow params, old flow data, context, current context, and up type, operation type. So we're seeing if we're changing probably. Cool. So this is nice. They just check that if it's not address 0, proceed. Then the agreement library .create callback inputs. I think I still have agreement library open somewhere. Callback inputs. Okay, so this is also a struct. And then this is the function that they're calling. Oh, so it just sets the struct. Sets that struct.
Any idea what a noop bit is? It's the last item in that struct.
No. Does anyone in chat know what it is? No, maybe like a no op bit.
Oh yeah, that makes sense. That makes sense.
Or I don't know. Let me think for a second.
No, let's get on. I just saw that and I was like, it's a funny name.
Yeah. Cool. And then, so yeah, it just sets the callback input struct. Yeah, uptype. So it's they get the states, and
I
then the not bit
see.
equals before agreement created noop, or before agreement updated noop, or before agreement terminated noop.
Oh, I see. It's again bitwise operations, I think. So it's like you were saying with permissions.
Yes, it's a bitwise. It's a bit permission setting. Yes.
Yeah.
Yeah. Yeah, it is. Cool. Then they get the call app before data. Sorry, call app before call data. Gosh,
Sure.
that's a mouthful.
That's
Which is this. It takes in the callback inputs, a memory, and a context. Cool. It has some local variables. So it has super app is jailed. When would an app become jailed?
I suppose if it does something that the flows don't like, or
Yeah, it probably breaks some state thing, and then
yeah.
And then a noop mask. So now we're going to start masking on those bits, those permission bits. So you take the app of the caller, get app manifest. And then if it is a super app and it's not jailed, so it's a valid super app, then you push callback stack. And if noop mask and inputs.noopbit is equal to 0, so that's probably like no permissions.
Yeah.
Then okay, we encode these these struct values, and then we
call back data.
and then it's before agreement terminated noop, and they set that when call app before callback. Wait, what? This is just a recursion in Solidity. I've never seen recursion in Solidity.
No ways. I didn't know you could do that.
Wow.
That's awesome.
Superfluid, you guys are cool. You guys are very cool. And then, again, then they pop the callback. So we push to the stack, and now over here somewhere.
Whoa, that just blew my mind.
We push the callback stack, and now we pop the callback stack back to 0.
Oh, my word.
Context should be constant. Do not modify it ever to ensure callback stack correctness. Yeah, wow. I think Myles and I are just a bit mind blown.
Whoever wrote that, you are a genius. And if you're listening to this, I'd just like you to know that. Yes.
We're happy that you exist. Cool. Now it sets the governance. We'll look at governance another day, I think. But if it is an app, apps have governance. Then we change the flow. So now we're doing an update probably. Should we look at this change flow function probably? Oh, wow. This is called a lot. So there's a stack there's change flow, total sender flow rate, total receiver flow rate. It takes in a current timestamp, app credit token, flow params, old flow data, private returns, deposit change, or delta, app credit base, and the flow data struct. Okay.
Interesting.
So they first calculate the deposit, which it's using governance. So they go governance.get. So the governance they first get here, and then they say get config as UN256, passing in the minimum deposit key. Remember that was that Ketchak.
Ketchak, yeah, that we saw right on top.
That hash, and then they round the number up for app credit. There's a caveat though, a condition. Now app could create a flow rate that is slightly higher than the incoming flow rate. The app may be jailed due to negative balance if it does this without its own balance. Rule of thumbs, app can use app credit to create the flow that has the same incoming flow rate, but due to deposit clipping, there's no guarantee that the sum, we saw that deposit clipping at the beginning, that the sum of the outgoing flow deposit can be covered by the credit always. It is advisable for the app to check the credit usage carefully and, if possible, always have some of its own balances to cover the deposits. Okay. And then they calculate deposit. Okay, we looked at that function. Then step 2, apply minimum deposit rule and calculate deposit change, delta. Okay, they minus that at that.
Yeah.
Add the O deposit makes sense. Then they get the new deposit by the adding the deposit delta, and then they cast that whole sum to a UN256. Now they check what the minimum deposit rule is applied, and they then calculate the deposit change and new deposit delta and deposit. Then they check that the credit is of the same token, and they check that it's not address 0. Then they set app credit base to 0. Oh, if it is. So first they check is a valid app credit token, and if it isn't, they set it to 0. So 0 just means no permission, I think, in this rate.
Yeah.
Cool. Then there's a tilde in here, so they update the current flow info. So new flow data is flow data, and they pass in. So if this is true,
yes,
then they set it to 0. Otherwise, current timestamp is 0.
Yes.
Then they set the flow rate, the new deposit, and they add the O deposit. Okay, leaving it unchanged for later adjustment. Wow. Then they update agreement data. Cool. So they've made this new flow data, and now they're updating it. By also encoding it. Then they now instantiate an instance of the change flow stack variables struct, and they call it vars. Not very verbose naming. And then they update the send and receive amount flow state with the changes. Cool. So that's just setting that struct basically and updating the count flow state. Then they emit flow updated events with these. Wow, I've never seen an event with this many parameters. And then they had this many. So they have a second one, an extension.
I've never seen 2 emits in one function. It's a day of new things for me.
Yeah, it really is for me too. Cool. But we were on the first change flow. Wow, we're not going to finish this today.
No.
Where are we? We're only on like line 200, and there's like
we're not even a quarter of the way through.
Yeah, gosh. We can go a bit over, but not much. So cool. So that's what they're doing here. Then they require available balance. Okay, this is just going to be a check that there is an available balance.
Yeah.
And this is almost like a modifier, but they're doing it here. So you can have an internal function that has a require in it.
That acts as a modifier.
Acts as a modifier. And the reason is they only want to do that now. Like otherwise, if they wanted to do it for the whole function, they would have just had a modifier at the beginning of the function. But if they only want to do it here, that's
cool. You couldn't put a modifier in the beginning of the function, right? I mean, in the middle of a function, right?
No, I don't think so. No, you can't. The whole function either has a modifier or not. So if you want to do it in the middle, you do it like this.
That's
very cool. That's a really cool tip. Yeah. Cool. Then that they check it's not address 0. They check that there's gas left, and then they do a try catch. Again, you don't see that often in Solidity. I bet you these guys are like C++ or Java native.
Java guys, definitely.
And then they just learn Solidity, and then they're doing like things like recursion and try catches. Cool. So they try this catching the out of gas.
There's the hook that we were talking about earlier. There's an onCreate hook.
Yes. Wow.
That's very cool.
Cool. Cool. And that's how you create a flow. Oh my gosh. Maybe this is actually a nice place to wrap up on.
Yes.
We'll just remember we're on line 485 for
Our
part
next
2.
function is update flow.
Update flow. Cool.
Yeah.
Thanks, Myles.
Awesome.
I really enjoyed chatting to you and going through this repo.
Yeah.
And thanks for watching. That's been another episode of Solidity Fridays brought to you by Linum Labs.
And we'll see you next week.